We are 1 minute out. We'll be starting soon. Hi, everyone. Can one of the panelists confirm that they can hear me clearly and they can see the screen?
Yes, you're fine.
Yes.
Okay, thank you. So let's start. Welcome to RFCs We Love. This is our first RFCs We Love of 2021. We will be focusing on data centers today. So this is our overall 20th meetup. We have been doing this for a couple of years now. And since we went in the lockdown and quarantine world and virtual world, this is our 7th fully virtual RFCs We Love. For those who are attending this for the first time, this is organized by IIESOC, which is India Internet Engineering Society. We do a couple of other events apart from RFCs We Love, which you are attending today. We do a connections event since 2017, which is a pre-ITF forum, which we used to organize in India. This time we did it after the ITF and in December. And I have some details about that as well. We have also starting an IPv6 webinar series, which will start from 4th Feb. So those of you who are interested in IPv6 deployment, please consider joining. I have a very small slide on that as well. So just usual, we usually start uh, 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 our RFCs. We love to just get a quick poll of folks who are new and just to get a reading of how many people who have been attending this, how many people are new. So we would like folks to just go to their Zoom, click on the poll and just do a quick poll. Oh, pretty good. So a lot of you are here for the very first time. So welcome. Thanks for coming. And I hope you enjoy this event and continue to participate in our RFCs We Love and other events that we organize. Thank you. I'll keep the poll open for a few more minutes so that people who are coming in late can also participate. Thank you. Thanks for polling. It's good to always see new folks who are joining today. Just a very quick news, something which I know some of you would be interested in. ITF 110 is from 8th to 12th March, is almost here. Again, ITF has been providing fee waivers. Otherwise, this online meeting does cost, but they have providing fee waivers. So for those who require fee waiver, please use this opportunity. Register for ITF 110. They are going to be in European time zone, UTC 12 to 18, so which will be around evening time to a little late night for us. So it's going to be still pretty good. It's on the timing that works for India. So please do participate. Note that we did a whole RFCs We Love focusing on helping people out, understanding ITF, how to participate in ITF. There is a link. What I will do is after my talk gets over, I'll post all these links in the chat as well. And of course, all the materials from today's presentation would also be available. So don't worry, all these links will be provided to you. This RFCs We Love had a pretty good session on how to start, what are the tips, and especially in the virtual world, now that ITF is fully virtual, fully online, what are the tips now to participate? So all that thing is covered there. I hope you will find this useful. Some another news from the ITF, we have a new ITF leadership. Normcom announced their results. Lars Eggert, who was earlier IRTF chair a couple of years back, is now the ITF chair. We have a little revamp in ISG, IAB, etc. So if you were not aware, look at the new results, and I hope you participate in the nomcom process as well. As I was mentioning, we did the connections event. This is our blog, which recaps the connection event. If you did not attend, here there's the recap, all the videos and all the slides are available. So please go through them and ask us for any feedback, suggestions. We are always open. Thank you. Now, I was talking about the IPv6 webinar. This is the detail there. This is a multi-year project where we are starting with the year one. Our year one focus is preparing good training material focused on IPv6 deployment and targeting universities, targeting enterprises where the IPv6 deployment is on the lower slide, and also deep diving what are the issues and what would be a template to follow to move from IPv4 to IPv6 in these infrastructure. So the webinars are going to start from 4th Feb. These are not just going to be webinars. We are following the webinars with a lab component as well. That means some hands-on experience. We will be using APNIC lab as well as some ideas of what you learn in the webinars. You also try it out and gets your hand dirty with IPv6 deployment. That's the idea behind these webinars. So I hope these will be very useful for anyone who is interested in IPv6. So please do consider joining us for IPv6 webinar series as well. These are the details. As you can see, we start from Feb 4th with introduction. We have a lab following week. Next month, we take up neighbor discovery, followed by a lab, address planning, transition, DHCP, V6, IPv6 in cloud, security, troubleshooting, and looking at Wireshark, all that useful things that are needed when you deploy and you need to figure out where the issues are, etc. So please do register. As I said, I'll post the link in the chat window once I stop talking. Okay, since a couple of you are new here, we do most of our work on our mailing list. ITF has generously provided us with an ITF India community mailing list. So please consider joining that. Otherwise, our WhatsApp group is quite active. So here's the link for WhatsApp group joining. Again, I'll post it in the chat. And of course, you can always email us directly. We are also on social media. So please do stay connected and spread the word so that more and more new people can join this activity. Okay, so without taking more time, if there are any questions, just use the Q&A, like a Q&A option in the webinar, and I will answer that question via text or even later on as needed. Thank you. So let's start with our main event, for which you guys are here. Welcome to RFCs We Love. This is our data center edition. We have two very good speakers today. We have Tony Lee and we have Nagendra. We'll start with Tony Lee's presentation on data center scaling, talk about how various things that are happening in ITF. And this would be a really interesting talk. So let's get into that. Followed by that, we have Nagendra Nainer from Cisco, who will be talking about virtualization and networking in data centers. So again, this is going to be a pretty interesting talk. So we are super grateful to have two amazing talks planned for you today. Okay, so let's start with data center scaling. Tony Lee, I think many of you who are involved in the routing space know Tony Lee. He's legendary. He has been involved in this space for over 30 years. He was critical. He plays a very critical role from the starting in BGP and CIDR. He has been involved with Cisco, Juniper. Currently, he's with Arista, and his main focus these days are on data center scaling, dynamic flooding, area proxy, all that stuff. So we are super excited to have Tony Lee for the first time participate in our event, and we hope this is going to be super interesting. So I'll stop sharing and off to you, Tony.
Thank you.
Sorry. 1 second. Why did it's just covering the screen? Yes. Did I stop sharing or my screen is still visible? Tony, are you able to share your screen?
I think I am.
Okay. Yes, I can see it.
Yeah.
Very good. All right. Thank you very much. Good morning. I'm going to be talking today a little bit about the work that we've been doing for Supernodes, and I'll explain a lot about that in just a bit. If you have any questions, please do not hesitate to interrupt. I would very much welcome this being a discussion, not just a talk. All right, getting into it. So data center architecture has been fixed for the last few years, but it's not always been exactly what we have today. Largely what people do today is all around BGP. And we sort of bumbled into this architecture. Leaf spine is very obvious, but BGP is not obvious. And we ended up in this situation because back when people were starting to build large data centers, the IGP implementations had a lot of issues. And because of those issues, people ended up rejecting using the IGPs and went off and started doing things with BGP. All well and good, but using BGP has some limitations of its own. It causes us problems, for example, if people want to do traffic engineering, because BGP doesn't carry enough traffic engineering information. So we wanted to sit down and explore and see what would happen if we went back and tried to fix some of the problems in the IGPs to see if we could build a data center architecture that was more scalable and used the IGPs as their basis. Now we ran into two real problems here. First of all, the IGPs do flooding, and in a really dense topology, such as a leaf spine topology, that flooding becomes excessive. And that becomes a problem because it causes what we call a congestive collapse. We also run into problems due to scale. Conventional wisdom in the early days of the IGPs meant that you could only have about 1,000 nodes in a single area. While that number has changed over time and grown substantially, there are still scale limits that we will always have because of the way that link state protocols operate. So how can we build much bigger data centers if we need to? So we wanted to try to address this. How can we reduce flooding and improve hierarchy in the IGPs so that we can scale to much larger data centers? Specifically, we wanted to address two things. In the control plane, we want to change the flooding algorithms. We're introducing a notion called dynamic flooding. And the idea here is to reduce flooding scale by limiting the flooding topology. Let's not flood on every link in the data center. We've got a great deal of redundancy in a leaf spine topology. We only need 2 copies of every LSP, so let's stop sending LSPs we don't need. Area proxy is an improvement on the ISIS hierarchy mechanism. The original ISIS hierarchy mechanism is somewhat awkward because it forces level 1 topology to be exported into level 2, and this causes scalability problems. What happens if we do a better job of abstracting out topology information and present a level 1 area as a single opaque node? So we'll talk about how we can do that. And then the third problem that we have to work on is in the management plane. We really need hierarchy. And what we're trying to do is to create additional hierarchical abstractions. And this is the most challenging thing that we've run into here. What we're working on is adding hierarchy in our own management product. And I'll talk only briefly about that, because that's actually non-standard yet. Okay. Again, what we're trying to do is to take an area or a large blob in the data center and represent it as one single atomic node. So what are the advantages of doing it this way? Well, if we do build supernodes this way, if we build data centers based on this architecture, we get a very flexible topology. Leaf spine is certainly the most common today. At certain scales, people go to a super spine, but frankly, we can actually be much more general than that. Any CLO topology certainly works well for the data center, and we can scale upwards using CLO topologies very, very rapidly to very, very high degrees. It's also nice because we've got a great deal of capacity flexibility. If you want to upgrade some of your links from, say, 100 gig to 400 gig, and then to 800 gig, those kinds of increments are possible, and it can easily be done on a link-by-link basis. So you can actually dial in exactly how much capacity you need and pay for it as you go. Provisioning is equally easy. If you need additional bandwidth, if you need additional nodes added to your leaf spine, well, that's relatively straightforward. And there is no known upper bound to how big you want to build out your network if you do this. Upgrades are equally easy. Because each node is independent actually internally, you can upgrade one node at a time, just as you would with a normal network. Of course, we want this automated, so upgrading things incrementally is always a simple and stable answer. A nice side effect of this is a reduced blast radius. If you have a supernode and you have a system that crashes, you're only taking out one node in your entire data center. You're not taking out an entire multi-chassis. You've got lower complexity. If you use multi-chassis, large multi-chassis routers today, the internal complexity of that multi-chassis system is very, very high. It's very difficult to make operate. And if you do choose to go to multi-chassis, that can actually be a member node inside of a supernode. If you do go to supernodes, you take an area, reduce it down to one node. If you have a large network, you can see that it takes a very large network, 60 nodes, and reduces it down to 6. This is very straightforward and wonderful for scalability. All right. So before we do that, the first thing we have to talk about is how to improve flooding. There are 3 internet drafts that I want to talk about. You see listed here. Okay. Dynamic flooding, and then our dynamic flooding algorithm, and the Yang model for dynamic flooding. So here's the basic idea. When we start flooding on a highly redundant topology, we end up with a lot of redundant flooding. And unfortunately, it turns out that it's really synchronized flooding. If you have an LSP update issued by one node and it floods it to all of its neighbors, and today in the modern world, most of the control plane has ample capacity, so all of its neighbors flood all at the same time. So all of the receivers start receiving n copies of every LSP all at the same time. This creates a flooding storm and creates a cascade failure that causes one node after another to be overwhelmed in the control plane and fail in a sequential manner. This can cause your entire data center to effectively come off the line and disconnect. Of course, as soon as this starts happening, it's very, very difficult to recover. You pretty much have to shut everything down and then bring things up one node at a time, and nobody wants to go through that. Now, the really annoying part is that we do not need the entire topology for flooding. All we need is a subset of it. What do we need for flooding? Well, we want to be able to address a whole variety of dense topologies. And obviously we want to cover leaf spine, but we have lots of different CLO topologies that are not, strictly speaking, leaf spine. Complete graphs are nice because they show generality. A complete graph is one where every node is connected to every other node in the network. That is the most dense topology you can have. We very much want there to be no single point of failure in a flooding topology. So the loss of any link or node should not hinder convergence. We want to limit flooding propagation delays. It would be easy to build a flooding topology that basically took every node in a leaf spine and put it into a giant cycle. But that turns out to not be very nice, because now when using propagate and LSP change, it has to make many, many hops before it gets to every node in the network. Okay, so what we want to do is to now find a small, tightly connected, but not densely connected topology. So we want to minimize the diameter of our flooding topology. And we still want to interact with the remainder of our IGP. While we have dense topology in the data center, we may have sparse topologies in other parts of the network. Because we have a WAN, we still want to be able to interoperate. So this is what we're trying to accomplish. Now we've got two proposals for how to do this. We have both a centralized and a distributed approach. And I'll talk about the centralized approach first. In this centralized approach, we elect one node as an area leader. And this election mechanism is very simple, very similar to designated router election. The election part there is simply run over the area database, link state database, instead of using just the adjacencies on a particular link. But otherwise, in principle, it's very much the same. This is a pretty proven mechanism. We've been using it for years and shows us very stable results. Okay. Once we have an area leader, then he's responsible for computing a new flooding topology. What part of the topology should we flood on? Just so we get every node, we have it in a redundant mechanism, but we aren't flooding too much. And the algorithm for computing this turns out to be fairly interesting. Once the flooding topology has been computed, the area leader then takes that, encodes that into the link state database, and distributes it throughout the area. Now, other nodes in the area can look at this flooding topology and decide which links they are going to flood on. Typically, a node is going to flood on only 2 links. If there is a topology change, the area leader will detect this because it sees link state updates, and it can compute a new flooding topology. If it does happen, the area leader changes the flooding topology it's advertising and updates its own flooding topology advertisements. If in fact a node does come up and is not connected to the flooding topology, and this happens, for example, if a node is just booting, then it can also request temporary flooding from its neighbors. A node comes up and says, "Hi, please flood to me," and its neighbors will temporarily flood to it until it's detected by the area leader. Then it becomes a topology change, a new flooding topology is distributed, and the situation is restored. You can also do dynamic flooding in a distributed model. You can do this in very simplistic flooding algorithms, but of course it becomes much more challenging to debug. It's harder to standardize and to achieve interoperability. All of the nodes in the area are going to have to make the exact same decisions. Now, we did this for SPF. That is how the link state algorithms work today. And we had lots of fun trying to make that interoperate. But we haven't been able to do that, or haven't even attempted to do that for any algorithm that's more complicated than SPF. Because the algorithms that we are going to talk about are much more complicated, we did not choose to take this approach. So we stayed centralized. We have a bunch of protocol extensions to carry this information around. First of all, we carry around a new sub-TLV for the area leader. This indicates a system's preference for becoming area leader. and it's the basis of doing the area leader election. Then we have a dynamic flooding sub-TLV. This indicates that a node supports dynamic flooding, and if it's going to participate in the distributed model, what algorithms it will support. We have area node IDs, TLVs. What we do here is to encode system IDs in a very simple way and try to make the encoding of the flooding path very dense. So we carry around a list of node IDs in one location and then use indices into this list when describing the flooding path. That flooding path TLV then becomes just a list of indices, and that's relatively dense. To support temporary flooding, we also have a flooding request TLV that can go in the hello packets, and that's a request to a neighbor to say, please flood to me. Pretty straightforward. This graph shows how this flooding topology improvements work. We took a look at and simulated what happens in leaf spine networks. The x-axis is the number of leaves in the network. The y-axis is the number of spines. And on the vertical or z-axis, you can see the percentage of improvement. You can see even at 4 spines, we're already getting 50% improvement in flooding. Half of our links are not being used for flooding. As we scale upwards, we get over 90%. We end up not using a whole lot of links because we don't need them. Plain and simple. We can take a look and see some of the flooding topologies that we might compute. This shows K10, a complete graph on 10 nodes. Dotted lines show links that are not being used for flooding. Solid lines show the flooding topology itself. Different colors indicate different iterations of the flooding algorithm. As you can see, we're flooding on very, very few links. If we look at leaf spine networks, okay, here we have 4 spines and 17 leaves. And as you can see, leaves flood on 2 and only 2 links. We can extend this. This is a super spine topology with 16 super spines, 64 spines, and 128 leaves. This would be a very, very large data center. And for this graph, we're not showing the links that are not used for non-flooding, only the flooding topology. As you can see already, that's dense. And if we showed all the other links, this entire graph would be black. If we take a look at something in the middle, this is a leaf spine network with 4 spines and 60 leaves. Again, you can see the leaves are only flooding on 2 links. And then, pretty importantly, we wanted to distribute all of the flooding across all of the spines. And as you can see, each of the spines is about evenly loaded. So we set this up in a virtual environment, and we went ahead and measured this. Again, this is a leaf spine network with 4 spines and 60 leaves. And when we boot this in normal flooding, we end up with about 110,000 messages sent to and from the spine, 15,000 per leaf. And then if we enable dynamic flooding, we can see that we reduce that. We only end up with about 41,000 messages at the spine and 3,000 at the leaf. Reductions of 62 and 77% respectively. This also includes IAHs. We weren't careful enough to filter that out. So this spec has been accepted as a link state routing working group item. That means that it's working slowly towards becoming an RFC. We have no outstanding issues at this point. We are waiting for waiting for deployment reports. So we would like people to use this and come up and go public and tell us how it's operating for them. We do have a Yang model in the draft. And if people want to comment on that, we welcome comments there. The Arista implementation is already complete. We've documented our algorithm, published that algorithm in an internet draft. This is implemented for ISIS, tested, and is already shipping. And our feature documentation is available on the web if people want to read it. There are 2 other implementations that I know about. Cisco apparently went off and implemented a proprietary algorithm. I have not understood the algorithm yet. Haven't seen any documentation on it. This appears to be a distributed algorithm for NXOS. And as far as I can tell, this only supports leaf-spine architectures. Huawei also has proposed an algorithm. I don't know what the implementation status of that is, but it also appears to only support leaf-spine. Okay. All right. Let me stop there for a second. I seem to have some questions. Let me see if I can look at those. Question 1, would data center lie beyond WAN or is part of the WAN? Well, that's a combination of things. Data centers do not exist without WANs. They are always going to have a large component, obviously, inside the data center walls, but all of that data eventually has to go somewhere. And usually there is bandwidth out of the data center into a larger part of a WAN. Now, how you architect it, people do that in a couple of different ways, and a lot of it is about how you model your organization. Sometimes the people who run the WAN are different than the people who run the data center, and you end up with 2 organizations and you end up with a routing boundary there. But that's not a requirement. If you have one group that's running both data center and WAN, they can merge and actually run them coherently. Next question. Is the cost of computing flooding topology going to affect convergence? No, the way we've architected our implementation, the flooding topology is computed after the link state database has converged and SPF has run. However, after we do compute the flooding topology, the area leader is going to have to flood any changes. And in flooding changes, that's going to cause another SPF run throughout the area. So it's going to add to the computational cost, but because it's not actually changing the topology, the actual forwarding topology, that's not going to actually change convergence. Okay, next question. Does Igmp play a role in the data plane for flooding? Only for multicast, and none of this pertains to multicast. Next question. Is there a convergence testing experience on BGP-based data centers versus optimized ISIS? I haven't done that. I don't know if anybody has. It would be interesting to know. We have not been out to test convergence time. We're just trying to see what we could do for scalability. Okay. Next question. Does flooding affect the performance of the data center? BGP can give better route filtering and control. How is this effective compared to BGP? Flooding should not affect the performance of the data center. Obviously, we want rapid convergence. We should get that intrinsically with both protocols. That's not really an issue. Route filtering and control, yes, if you want to do route filtering, it's very difficult to do with IGP. I don't recommend doing route filtering in data centers if you can avoid it. It adds to complexity. And if you're trying to do traffic engineering, there are better mechanisms for doing that with the link state IGP. Next question. How effective is this compared to Rift? I think I'm going to let Tony Pregenza answer that. He is the expert on Rift, and I am not. Tony likes to say he does link state down and distance vector up, and that greatly reduces flooding, and I certainly believe that. He also, in asking us to endorse Rift, is creating an entire new link state protocol. And link state protocols do take a while to mature and standardize and become interoperable. And that seems like a very, very expensive way to pay for solving this particular problem, especially since we have a pretty good solution with dynamic flooding. Any other questions? Okay. What are the security considerations of supernode architecture? No new security considerations here. All of this is just the exact same security architecture that you need to use for a link state IGP. Nothing has changed about this whatsoever. And yes, there are lots of security issues with IGPs, but I assume you know about how to deal with those. All right. Moving on. All right. Let's talk about area proxy. This is another draft that we're working on. This is already circulated.
Tony, I don't see your screen. Are you sharing it?
1 second. I have to push all the buttons in the right order.
Yes.
All right. All right, is that good?
Yes, Tony, go ahead.
Very good. All right. So the basic idea here is, again, we'd like to scale our link state database by doing better abstraction and data hiding. And as I mentioned earlier, right now, when we have a level 1 area and we want to use it for transit for level 2, we have to push all the topology information into level 2. That means that level 2 ends up with all of our topology in it, which is not very scalable at all. We're effectively running one giant area. So instead of doing that, let's suppose that we create a single proxy node. And it's going to take the place of the entire L1 area in level 2. The level 1 area could be a supernode. It could be an entire POP. It could be a data center. It could be any big chunk of the network that you like. What we'd like to do is to have level 2 grow linearly with the number of POPs or the number of areas, not with the number of routers in the level 1. So take this network you see here, it's got 60 routers. We'd really love for there only to be 6 entries in level 2, not 60. All right. So I was talking about how legacy areas work in ISIS. Right now in ISIS, if you've got a level 1 area and you're trying to provide transit topology, a transit service across that level 1 area into level 2, you have to take all of those links and export them into level 2. This is the way the protocol was designed long, long ago. Well, in some cases, that's fine. If your level 1 topology is relatively sparse, if there are a few backbone links that you need to advertise, that's probably not a big deal. But if your entire level 1 data center is used for transit, what happens? Everything ends up exported into level 2. all of the links you see here transiting a small level 1 area end up in level 2, and you end up with no scale savings whatsoever. The basic ISIS level abstraction mechanism is suboptimal in a lot of cases. So let's take our level 1 area and have it emulate a single router. Boom. Okay, now I've got one router there. It's still got the same external links, and I've hidden all of the internal topology and scale. Now I can't tell if there are 10 routers inside or 1,000, and I don't care. Okay, so how do we make this work? So the first thing we're going to do is imagine that we have a proxy node. And this is a virtual node. There is no hardware for it. We're going to assign a proxy system ID to the proxy node. This is easily done. We already make up system IDs for all of our nodes in an ISIS network anyway, so we're just asking the network administrator to allocate one more system ID value. We're going to distribute this proxy system ID to all of the edge routers in the area. And the edge routers are going to propagate and send all of their information to their external neighbors using the proxy system ID. So when they send hello packets, they're going to be sourced like they came from the proxy system ID. Now we're going to have the area leader, and we're stealing the area leader concept from dynamic flooding, same mechanism we talked about back there. We're going to reuse that and have the area leader generate a proxy LSP. This is the description for the topology around the proxy node. And the area leader is going to pick up all the information in the link state database and look at the level 2 information that all of our internal edges have picked up. And it's going to include adjacencies to all of our external neighbors. It also wants to include all the prefixes internal to the area. We want the address space within the L1 area to be reachable, even if we don't want to carry around the topology details about it. All of this goes into the proxy LSP, and then the proxy LSP, and only the proxy LSP, is flooded outside of the area into the rest of level 2. Okay. All right, that gives us exactly this abstraction we were looking for. Here's our proxy node. He's got 8 adjacencies. That's it. You can't tell anything more. It's a node. The good news is we can also do traffic engineering. Okay, if we were already doing level 1 traffic engineering, only inside of level 1, and we want to continue, that doesn't change. We haven't changed level 1 traffic engineering or level 1 routing at all. If we're doing pure level 2 traffic engineering, okay, proxy node now advertises its own node SID. So for SR purposes, it looks like a node. Okay. Again, the level 1 topology is not visible to level 2. So if you're trying to do computations across level 2, across the area, but you were expecting to use the level 1 topology, you're not going to be able to do that anymore. If you're using RSVP, you're going to have paths to addresses, and what they were when they were previously a strict hop that may refer to several level 1 nodes, you're now going to need to make it loose hops and only refer to level 2 nodes. If you're doing traffic engineering on both level 1 and level 2, then you need topology information from both level 1 and level 2. And you probably already have a controller doing this. And the good news is the controller can probably see level 1 and level 2, so the controller already has full information. In fact, the only thing the controller needs to do is to ignore the proxy node. If you are operating without a controller, then you've got some problems. You're going to have problems for level 2 nodes to compute detailed paths because they can't see inside of the proxy area. Okay? So that's the one place where there's problems. Fortunately, that's a pretty rare problem. So again, if we do this, we start off with 60 nodes, it becomes 6. And our network now scales. The LSR working group has accepted this document as an experimental draft. There's some competing drafts from Juniper and Huawei. All of us are waiting to see how the market picks up and responds to various proposals. And so we're waiting for feedback from people. The Arista implementation, that's done and tested in the lab. System test is completed, and this shipped already. And again, our documentation is available on the web already. Okay. So dynamic flooding, area proxy together creates supernodes and will allow us to scale networks much more easily than we ever have before. And it's a nice architecture. It's multi-vendor, so you get competitive pricing. It gives you elastic capacity. You can grow it as you need it in small increments if necessary, one link at a time if necessary. It's scalable. We know how to build very, very large topologies, and it's topology independent. So as we roll out terabit Ethernet, we'll be able to use that immediately without restriction. It's easily upgradable and gives us lots of isolation. When something crashes, it'll be a single chassis. That's a big improvement over losing lots. All right, that's all I had today. Thank you very much.
Thank you, Tony. We have one question. Other people also, please use Q&A to ask questions.
Since the L2 nodes have only prefix readability and not the entire L1 topology, wouldn't the paths computed by L2 nodes for L1 prefixes be suboptimal? Absolutely. One of the problems that we have is when we go and create abstraction, we lose information. So when you compute a path using across a proxy node, you will be able to see a metric. The metrics going to the node and away from the node, the proxy node, are still there. But you can't see any metrics inside of the node. And so you may end up sending more traffic through the node. You may have to change metrics to achieve your desired results. You may also have to use traffic engineering. This is one of the prices you have to pay, yes. Are there any other questions? Cool. Thank you very much.
Tony, let me ask you one question, just a meta questions in some way, because some of the people who join our webinars do not follow ITF regularly. And they, especially in this area, gets confused by the number of things that are happening, like Rift, LSVR. Even the person who follows LSR working group get confused because of the number of proposals in this space. So at the ITF level, if you can guide, like, what is the process here? How would this work out? How do you see all of this stabilizing a little bit?
So I've been at the ITF for 30 years now, and you're right, there's a lot going on, and it can be very, very difficult to understand what's important and what's not. The good news is that the process moves pretty slowly. So it's unlikely that something gets by you that you don't notice as important. How is this going to shake out in the longer term? I don't know exactly. The ITF is not very good about making decisions in and of itself. It's only been useful when it was trying to standardize de facto standards, things that people have already agreed that they're going to use. And so it really becomes a question of what the market wants and what other companies are going to implement. If these ideas are useful and they implement them, and at least for dynamic flooding, you've seen some other implementations start to happen, we may actually see some interoperability. And if that happens, then it will move forward and standardize.
Thank you, Tony. Thanks for a great presentation. Thank you. Let me share my screen. Okay. Yes. So next, let's moving right ahead. Yes, we are almost on time, so that's good. Next, we have Nagendra Kumar Naidar from Cisco. He's the part of Cisco Customer Experience CX team. He's been involved with enterprise business vertical for a long time. He has been involved in ITF, in virtualization and container space, as well as has multiple patents. In fact, patents more than 100 in this area. He has in fact written 2 technical books in this field as well. So we are again very, very grateful for Nagendran to be a part of today's event. So off to you, Nagendran. Nagendran, could you share your screen now? And you are on mute as well.
Can you hear me now?
Yes.
Okay.
And I can see your screen.
All right. Thank you, Dhruv and Kannan, for this invite. I'm really excited to be here. So I'm Nagendra. I'm one of the principal engineer with Cisco, like Dhruv mentioned, as part of CX organization. I've been participating in the ITF for nearly 10 years. Had the privilege to be part of different protocol and OEM design teams. I also co-authored and produced different, standard RFCs. And I'm also part of the Ops Directorate review team. So IETF and RFC are really, really close to my heart. And when I got this, opportunity to deliver a talk in this forum, I really got excited. I don't want to miss this. So once again, thank you, Kannan and Dhruv, for this opportunity. So the topic that we'll be discussing in this session today is about is a kind of endowment of virtualization, like how the abundant availability of compute resources in the data center could be used, particularly in the data center switches, could be used to host some network applications or functions to perform certain operational and related activities. So I devised it in a way that we'll start by sprucing up the basics of virtualization, and we'll be looking into what is virtualization in the data center, and then we'll see how the open source tools that are available in the industry, along with IETF produced standards, could be used to develop the application that can be hosted on the data center switches for operational activities. We'll then look into a couple of example use cases. So that said, before jumping into the nits and grits of this talk, I'd like to take a moment to acknowledge some of these gentlemen, some of these experts, basically. Throughout this presentation, I tried to include the references to different RFCs that are directly or indirectly related to this topic. So I would like to take a moment to thank all those authors. As you know, it normally takes few years to produce an RFC. So there's a tremendous amount of time and effort that are put into this, producing these RFCs. I also would like to thank Yogesh Ramdas, who's my colleague and a very good friend of mine. So Yogesh and I co-authored a technical book that was published last year, which is on the same topic, like how can we develop and host applications on the service provider or enterprise or data center switches and routers. I also would like to thank Chris and Madan, who helped us develop some of these applications that we use for demonstration, the use case demonstrations. So that's it. Let's start with the definition of virtualization. So virtualization, by definition, is the ability to create a virtual instance or a virtual versions of something. It could be a server, or it could be a function, or it could be a network. It could be anything. So virtualization, as we know, is a buzzword that we are aware of in the past, 1 or 2 decades. But interestingly, the concept of virtualization basically dates back to 1960s, when IBM Research Center, they developed a hypervisor called control program, which allowed the users to instantiate different instances of virtual machines. So back in 1960s or 70s, the computing resources are really costly. So it's not affordable to have the researchers or any other engineers to have their own dedicated compute resources. So they have to rely on different, time sharing and other dial-up methods to, log into the compute resource and use it on a sharing basis. So around 1970s, virtualization is one of the real hot topic, and there are even different, international conferences and other IEEE conferences that were dedicated for the research in and around virtualization. But as we start seeing the transistor-based processor, the price of these computers, started coming down, and obviously the interest on virtualization started to fade away. But it started again, to gain attention around the late 1990s, of course, with a totally different motivation. So virtualization, I personally think, is one of the transformational or enabler technology that resulted in new technologies or new business verticals, or even allowed us to help realize the benefits of other technologies. For example, the cloud computing and cloud storage. So these are some of the technologies. I wouldn't say it's not possible, but it's nearly impossible or really difficult to realize the actual benefits that we are enjoying today without the underlying concept called virtualization. And the same goes true for other buzzwords like, NFV or SDN. So NFV is about, disaggregating the network functions so that we can run those network functions as a virtual entity. And SDN is about, decoupling the software from the underlying hardware so that the control plane or the software could be hosted as a virtual entity. So all these buzzwords that we are, reaping the benefits today are a result of the underlying concept called virtualization. So back in 1970s, the motivation was pretty simple and pretty clear. How can we reduce the cost? But around 1990s, late 1990s, when we start gaining attention again on virtualization, there are additional motivation. For example, in this digital transformation world, in a business enterprise or any business, it's really simple to see a lot of business applications which requires its own dedicated resources. And as a part of best practice or even compliance purpose, it's common to see those servers or the application running with a maximum of 60 to 70% of resource utilization. This is to give enough room for some unexpected behaviors. Like, for example, if there is a surge in the utilization, or if there is a DOS attack, or if there is any other unexpected behavior, we'll have some resources that could be used to handle that. So now imagine with thousands of business applications that are required to have their own physical servers, it's really not possible. So how can we efficiently utilize those resources? The next one is about resiliency. In this fast-growing world, failure of a business application is something that's not acceptable for the business. So the simple thing to have high availability is to have multiple instances of the application, and to avoid single point of failure. It is common to see that we'll be running those applications in different servers, physical servers. So again, it falls back to the same problem, which is like, how can we efficiently utilize the resource without compromising with the high availability? The third one is about simplicity. In the world of physical servers, it normally takes few months to move an application to production. It starts right from gathering the resource requirement, like what is the CPU or memory requirement for this to run this particular application, and then procure it, put all those pieces together to build the server, and then install the operating system, and on top of it, all the required libraries and binaries, and finally the application. And then we do the operational, basic functional testing, and then the performance testing, and finally we move it to production. So it really takes you months to move the application to production. So how can we, efficiently or make this easy? How can we make this deployment easy? And it's not just about the initial deployment. Even with workload migration, if we were to migrate the existing workload from one location to other location, we have to go through all these challenges. So how can we make this simple? And finally, of course, the cost optimization. How can we reduce the number of carbon footprint? And how can we reduce the operational expenditures? So these are some of the motivation for virtualization that started gaining the attention again around late 1990s, that resulted in different technologies that we are actually enjoying today. So these are some of the types of virtualization. The first one is full virtualization. where we have a hypervisor layer that acts as a median or a translator between the guest operating system and the underlying hardware. So this hypervisor will act as a translator, handling all those hypercalls or other instructions between the guest operating system and the hardware. So the guest operating system could be natively hosted. There is no customization required on the guest operating system. While on the other hand, with para-virtualization, we don't have a hypervisor layer. So the operating system needs to be customized so that it can handle the hypercalls or other instructions to with the underlying hardware. The third one is hardware-assisted virtualization, which is nothing but the full virtualization with the support from the hardware or the processor. Most of the existing processors like the Intel VT or AMD V or even other processors that exist in the market, they support virtualization at the processor level. So there is a significant improvement in terms of performance when the virtualization is supported by the processor. Whoever have tried the running virtual machine in a server where the processor doesn't support virtualization, you may find way to instantiate that virtual machine, but the performance will be really, really poor. And the fourth one is nested virtualization. As the name says, this is nothing but virtualization on virtualization. So we'll have a hypervisor on top of which we'll have a virtual machine instantiator. And in the guest operating system of the virtual machine, we'll have another layer of virtualization, like a hypervisor. And on top of it, we'll have multiple instances of virtual entities. So arguably, this type of virtualization, there are different arguments around, is it really useful in the production network? But I personally think there are different use cases that could benefit with this nested virtualization. So what is virtualization in the data center? The first one is server virtualization. So this is one of the first and also the predominant use of virtualization, where the server workload is converted into a virtual instance, and we can run this as a virtual machine in any of the supported hardware or the server. So with the introduction of, like I said, the introduction of virtualization support in the underlying processor, the performance is much better. That we won't see any difference in terms of performance while running an application as a virtual machine versus running it in the physical server. So there are different types of proprietary and open source hypervisor that are available in the industry that could be used by, some are free to use, of course, if it is open source, that could be used by anyone to instantiate the virtual machines. Examples are Zen or KVM, Hyper-V, virtual boxes are some of these examples that we could use to create virtual machines. Now, each of these virtual machines will have its own guest operating system, on top of which will have the application hosted. Now, this is not the only way of virtualizing the server workload. There are other ways. This basically is an evolution. So there are other ways, where the next one is about containers. While the virtual machine, each of the virtual machine have its own guest operating system, the container is basically a kind of package that comprises of the application and the associated binaries and libraries that are required to execute those applications. So unlike a virtual machine where we have a dedicated guest operating system for each of those VMs, the containers, they share the guest operating system. With the use of container manager like Docker or Rocket, will be able to host different containers by sharing the same operating system. So the containers are a lighter weight version of server virtualization while comparing to virtual machine. Now, again, like I said, this is an evolution, so it didn't stop here. I didn't include it in this presentation, but I thought I'll also talk about the other variant, which is function as a service or serverless computing. So it took one step further, where we'll just have the function code, and we also will have a pool of hot or cold containers. So when the function router or the Lambda receives an incoming request to execute the function, it selects one of the container, the hot or cold container from the pool. It gets the function, load it, and execute the task. And once it is done, it will release the resource. So unlike containers or virtual machines, where irrespective of the usage, they are always on. The function as a service is something like the compute resource will be used only when there is a demand. So the application which are like sporadically used, they are a very good use cases for function as a service. So in a empirical data center, it's pretty common to see a combination of all these three. We can see workloads running as virtual machines or containers, or even even though we may not be seeing it now, in future we might be seeing the function as a service as well. So the next type of virtualization in the data center is network virtualization. So in the previous slide, we saw that we can have different instances of workloads running either as a virtual machine or as a container, and even we could have these combination running in the same physical server. So if these virtual instances belongs to different customers, and if it is distributed between different physical servers which are connected through a layer 3 fabric, how do we ensure that we offer privacy and security, and yet we provide an isolated network environment in a way that these distributed workloads that belongs to the same customer can communicate among themselves? So the very simple option is to virtualize the network devices. So instead of having physical devices, why not virtualize those switches, for example, here, and host the switch as one of the virtual entity in the physical server, and on a per customer basis, and connect the respective workload to the virtual switch. This is, of course, a viable solution, but the introduction of virtualization actually, it basically introduces different challenges and opportunities. Good examples are like the rapid provisioning or virtual, the VM mobility. We could have a workload which is hosted on one physical server, but for one other reason, it could be hot moved or cold moved from one server to another server. When we do that, how can we retain the connectivity? How can we retain the IP address that was assigned to the virtual machine? So in a way, we might be moving the workload from one physical server to another physical server, which are connected through layer 3 fabric, and yet we may need to retain the layer 2 connectivity. So this is more like, how can we retain layer 2 over a layer 3 fabric? So this is one simple challenge that I was mentioning. RFC 7364 consolidates different such problem statements that are related to how we need the network virtualization over such layer 3 fabric. And RFC 7365 defines the framework that basically creates the solution for this problem, and different overlay based encapsulation and the associated forwarding semantics have been proposed. RFC 7348 defines VXLAN as the overlay, which introduces VNIs to differentiate different tenants. And 7637 defines the network virtualization using GRE extensions. And 8365 defines EVPN for network virtualization overlay. There are also other work in progress, like for example, the SRv6 or segment routing that also could be used for the same purpose. Just like server virtualization, even network virtualization is more like an evolution. So back in the old days, we had physical appliances, which is nothing but a vendor proprietary operating system running on top of vendor proprietary hardware. So the very first step in network virtualization is to disaggregate this, the software disaggregation. By disaggregating the vendor proprietary operating system from the underlying hardware, we can run this operating system or the software as a virtual entity on any supported hardware. Simple examples are, as we saw in the past, virtual switches or virtual routers or virtual firewalls. Now, if you look deep into the routers, it's an assorted list of different network functions. So the next step in network virtualization is to disaggregate those functions and run each of those network functions, or at least a combination of different functions, as a standalone virtual entities, virtual machines. Now, the next one as part of this evolution is cloud native, where we followed microservice-based architecture, and so we can develop these network functions as containers and could be hosted anywhere using the container managers. So motivation for running the application on the network devices. Why do we need to run the applications on the network devices? So by leveraging the virtualization capability, like we saw that we'll be able to instantiate the functions either as a virtual machine or as a container or even as a function as a service. And also the ability to disaggregate the network functions along with different IETF defined standards, it basically opens up the gate for innovation. We started seeing an explosion of different application, which basically either pull the data from the network or push the data to the network for different sort of activities, like get the data, telemetry data, and do some sort of analytics, or push some data for configuration and other purpose. These are some of the example applications. Like for example, Wireshark could be used to sniff the packet that are pointed to the CPU and perform some basic anomaly or basic check. We also have different other applications, packet generator applications like T-Rex or Ipv6 that could be used to generate different types of probes, performance related probes, or even different types of packets, traffic. This could be used either to measure the performance between different devices in the network, or even it could be used to generate different types of traffic and see what would be the behavior of the network or the network device. Would it crash, or is it able to handle the device, handle the packets, etc. We also have different leaf applications like DNS or DHCP, and in a very sporadically utilized scenarios, instead of having a dedicated hardware to host these applications, this could be directly hosted on the network. And finally, we also have Prometheus or other visualization where we collect the telemetry data and we can visualize it using Grafana or others. So we do have different types of application that basically either pull the data from the network or push the data to the network. So would it not make sense if we move these applications as close as possible to the data? And when I say data, the data is actually in the network devices. So would it not make sense to move these applications directly on the devices? This is one of the primary motivation for running those applications directly on the network, not with devices. Now, if we take one step back and look into the existing data center switches, or in most of the white label and other devices that are available in the market, most of them are Linux-based architecture. So when it is Linux-based, it natively comes with some virtualization support. We can create different namespace for resource isolation, or we could enable different daemons like libvirt so that we get the virtualization support. We could install Docker so we can get the container manager to host the functions as containers. It also comes with different tool sets like Python or TCP dump that could be used for different purposes. So why not leverage this existing capabilities and leverage the capability of virtualization to host those applications directly on the network devices, so that we can bring the application as close as possible to the network data. So this is a closer look of how it looks in the data center. So like I said, we have this forwarding ASIC, which takes care of forwarding the traffic, and these devices have their own Linux kernel. By installing Docker or the KVM extension, we get the ability to host any of those network any of those functions. So IETF work hard in the past, for nearly around 10 years. There are a lot of works around getting the data from the network, the telemetry extensions, or network programming, the Yang data models and netconf. So using this, we can create application that have the ability to talk to any any devices in a vendor neutral manner. It's not anymore required to create application on a per vendor basis. Rather, thanks to IETF, these by using this network programming extensions and the telemetry extensions will be able to develop one application that could talk to multi-vendor devices. RFC 6020 defines the Yang data model, the format, which is 1.0. And 7950 introduces additional things like the RPC, and so we call it as Yang 1.1. 6241 defines the netconf, the transport for Yang data models. So there are also other RFCs which are related to this. So anyone interested to know more about this, feel free to read these drafts to have a better understanding. So this is an example of one of the examples that we capture from a data center switch. As you could see here, we used Docker to host the application, and we don't need to use any vendor proprietary CLIs. Rather, we can reuse the same Docker commands. once we have this Docker installed on the relevant Linux distribution, we'll be able to use the same command. So this is a capture that we took from a data center switch to run a Alpine-based Linux container. So we could have any of the applications. We could create an application based on certain Linux distribution, and using Docker, we'll be able to convert this into a Docker image by defining the base image as application, and then the set of binaries and libraries that are required, and finally the default command, and convert this into a Docker image, put it in the hub, and so we can download it to any of the network devices, and we can host it using this Docker command. Now imagine in a data center, like even Tony was mentioning, we are expecting a lot of devices, not just within the data center, even also the data center. If we were to host it manually by logging into each of the devices, it's going to be a bit hard. So is there any other way where we can do it in a much simpler manner? So there's something Kubernetes is one of the a well-known orchestration tool that is available to host containers. The good thing is, by having the right set of components installed in the network devices, we'll be able to make the network device register the compute resource as the worker node as part of the Kubernetes cluster. So this is an example of what we did in one of the switch. We installed the relevant components like the Docker and the kubelet and kubeproxy along with the kubeadm on one of the switch. By this, we can have another virtual machine that is acting as a Kubernetes master. We get the token from the Kubernetes master and run the kubeadm command from the data center switch. So it registers with the master and register itself as part of the cluster. So with this, we have one place from where we can orchestrate the entire container instantiation. We use the Kubernetes master to control what application we need to host and where in the network should we host it. So it makes it a lot more easier while comparing to the manual way of doing it. Instead of manually logging into each of those devices and execute the relevant Docker or related command to host the application, but by leveraging this open source, the Kubernetes orchestration, it makes it really, really simple to host it. And in fact, Kubernetes also takes care of if a container was hosted and for one other reason, if it is, if it failed to come up, Kubernetes will ensure that it keeps trying and ensure that the container is actually up and running. Now we saw that one of the primary motivation to run the application is to bring it as close as possible to the network data, so that it can collect the network data from the network device and do some sort of analytics or anything as the application says. That doesn't mean that the application is not required to communicate to the external network. There are different reasons why the hosted application may need to talk to other devices or other entities in the network. For example, we may have an application that basically collects the data from the device, do some sort of analytics, and may have to send it to a centralized analytics server for a holistic view of the entire network. Or even it could be another application which collects the data from the network device, do the analytics, and send it to a visualization server. So in order to do these things, the application that is hosted on the switch may require to have external connectivity. So these are some of the models. There might be other models, but these are some of the models that I'm aware of I played around with. That basically helps us to bring this connectivity for those hosted application. Routing model, unnumbered, shared IP, and layer 2 model. And if we take one step back, these are the high-level classification where we have shared model and we have dedicated model. So in the shared model, any of those applications that are hosted on the switch will share the network interface and the IP address from the hosted switch itself. So let's assume that we have a switch with 3 different interfaces, and we have multiple containers or application hosted on the switch. So each of those applications will inherit the interface and the IP address, all those IP address from the switch itself. If we were to log into the application and execute IP netns or ifconfig, we can see all these interfaces along with the IP address reflected in each of those applications. So when a packet is sent or received, the destination address alone may not be able to differentiate if the packet needs to be consumed by the host, or if it needs to be punted to one of those applications. So we may need a combination of destination and the port mapping that could be used to identify which application the packet basically belongs to. The next one is a dedicated model. As the name says, each of the containers or each of the application will have its own dedicated IP address. It either can have its own from one subnet, or it can have its own subnet. So in case of one subnet, it's more like a layer 2 bridge to which all the containers are connected, and we'll have one virtual interface from the host, which is also connected to the layer 2 bridge. If it is on a per subnet basis, it's more like a virtual point-to-point connectivity from the host to each of those applications. So we'll look into each of those models in detail, just to have better clarity. So the first one is routing, where the hosted application, again, this is part of the dedicated model, where we'll have a dedicated IP address for each of those hosted application. So for each of the application, we create a virtual interface, and one IP address will be assigned, and another virtual interface will be created on the host, and they both will be having the address from the same subnet. It either could be from /30 or from /24. Like I said, the multiple, if we have multiple containers hosted or application hosted, they either can belong to the same subnet, or it could belong to different subnets. The traffic originated, because they have their own dedicated address, any traffic originated or terminated to the application can be easily classified, as long as the host advertised the subnet. In this case, 10.1.1.0/24, as long as it is advertised outside the network, and the other devices can send the traffic towards this host, the 10.1.1.2 can be used to identify that this packet needs to be punted towards the application, wherein if the packet is to be consumed by the host, it either will be receiving with 172.16.1.1 or with 10.1.1.1. So the next network model is unnumbered. This is another dedicated model, and almost similar to the routing model, with one minor difference. So instead of having a dedicated IP address for the virtual interface on the host will be sharing the address with one of the physical interface. So as you could see in this interface, the WAN circuit have 10.1.1.1/24, and the virtual interface also have the same IP address, 10.1.1.1. The containers will have their own dedicated IP address, which is allocated from 10.1.1.0 subnet. So one thing that we need to be sure here is the address assigned to these containers or the applications hosted should not overlap with any of the address that is assigned in any external network that is part of the same subnet. So that's one thing that we need to be very sure about. Any application that basically originates this will again use this 10.1.1.2. So this address can be used to identify if the packet needs to be consumed by the host, or if it needs to be punted to the application. So next one is shared IP. This is similar to the Docker host networking. As I mentioned earlier, the application, hosted application will have the same interface and the IP address as like the host. So we need some sort of port mapping. By using a combination of the destination address and the transport layer ports, we can identify if the port needs to be, if the packet needs to be consumed by the host, or if it needs to be forwarded to the containers. And finally, we have this layer 2, where the underlying switch will act as a layer 2 switch. There is no routing here. Rather, the hosted application will be directly connected to an external router. Now, the application that we are hosting, either they can belong to the same VLAN, or we can have different VLANs. So in the former case, we may need a trunk between the switch to the external router, and in the latter case, we just need a switch port with the respective VLAN configured on the interface. So this is not just the network model that is supported. When Docker is used, we also can use the natively supported, the Docker supported network models. The moment when we enable Docker, by default, a default Docker bridge will be created, Docker 0. This is not just it. We can also create different user-defined bridges. And while instantiating the container, we can define which network does it belongs to. Should we assign it to the default bridge, or should it be one of the user-defined bridge, or if it should use the host networking. So Docker, when using Docker, we can use any of these Docker-supported network models as well. So there is one interesting topic that that was brought in when we were discussing this topic with some of the experts. Like with the introduction of CNFs, the cloud native and the microservice-based development, can we develop an application that could be hosted on different networks in a way that the data collected by the application may need to be steered across different devices, and the respective treatment needs to be applied on the data. So it's nothing but service function chaining. Right from around early 2014, IETF was working hard to produce different standards about how we can apply an ordered set of function to a packet. By leveraging this architecture, we can achieve what we were mentioning here, like using the CNF distributed across different devices. So RFC 7665 defines the architecture, the service function chaining architecture, and the RFC 8300 defines the network service header, which is another overlay header which defines the service index, the service path identifier, and the service index. A combination of these two basically identifies what is the ordered set of function that needs to be applied, and what has been applied, and what is next that needs to be applied. So with this, we can, even though this may not be available now, nothing stops us to develop an application and leverage those existing capabilities that are developed by IETF to realize what we are shown here. Like distribute the function among different devices, collect the data from one network device, and send it over other functions to apply different types of treatments. So let's now look into a couple of use case examples. This is one of the example related to data center switch. So Floodlight is the application. This is available as a Docker image. So anyone, if you're interested to play around with this, feel free to get this from Docker Hub, and you can host it and play around with this function. So this is a function. Once we use Docker to host it, there are two sub functionalities that happens. So the first one is it extracts the data, it collects the configuration from the network, and convert that into the list of features that are enabled from the configuration. And then it will identify what are the, based on the enabled feature, what are the control plane packets that are expected to be seen or to be pointed to the CPU. For example, if it is a pure layer 2 switch, none of those control plane packets are expected. The layer 3 control plane packets are expected to be pointed to the CPU, for example, OSPF or BGP. Wherein if it is a layer 3 switch with OSPF and BGP enabled, then we are expected to see any control plane packets related to OSPF and BGP, but not about other protocols. For example, if we don't have multicast enabled, then we don't expect PIM or other related control plane protocols. So the functionality will dissect this and identify what is expected based on the feature enabled. What are the control planes that are expected to be pointed to the CPU? The next functionality will basically leverages Wireshark. So it keeps sniffing the packet from the in-band port. So the in-band port is the one which is used to forward the packet towards the CPU. So it keeps sniffing this in-band port to gather all the packets and convert that into a JSON file to do a basic comparison. So we do have the data which says what is expected to be pointed to the CPU, and we also have the data which is about the packets that's being pointed to the CPU. By doing a simple comparison, we know what is expected and what we are seeing, and this could be used to detect simple anomalies. We can proactively detect what is happening in the network rather than waiting for some user complaints like high CPU and then jumping into the call to troubleshoot and identify what's being pointed to the CPU. This is more like the application is doing on our behalf, and keep notifying the operator that, hey, you know what, according to this configuration, I'm not expected to see these kind of control plane protocols being punted, and I'm seeing at this rate. You may have to further look into it to see why you're getting this. So this is a simple anomaly application that could be hosted on the data center switches to ensure what is being punted to the CPU is really expected based on the configuration. This is another example, which is related to path liveliness check or performance measurement. So I won't take the credit for TVAMP. I remember seeing it, different variants available in the Docker Hub. So we could collect the image from the Docker Hub, and it could be hosted. So the data center switch, on one of the switch, we hosted it as TVAMP server, and another switch we hosted as client. And we started sending the control packet and the test probes to measure the performance between different switches. Another test that we did is using seamless BFD, where we generated two different Docker images. The first one is the reflector base, and the next one is the client base. So seamless BFD is a variant of BFD, which uses or which can be used to perform a one-way liveliness check in a very scalable manner. We don't need to create multiple state entries on the reflector side. So this is a simple and a very effective use of BFD. So we tried creating a prototype of converting that into a container and host it in one of the switch. The reflector base was instantiated in one of the switch, and we had different clients running from different servers or different switches to continuously monitor the liveliness of the switch. As long as the switch is up and running, the reflector session will ensure that the control package, the BFD control package received or reflected back. And if the switch is down, the BFD session fails, and so they will be able to rapidly detect that the remote node failed. Now, using a combination of Kubernetes, this could be used to dynamically instantiate either the reflector base or even the TVAMP, the server and the client in different part of data center switches to proactively detect any performance degradation in a very scalable manner. So in summary, we do have a lot of capabilities that are introduced by virtualization and the ability to disaggregate the network. And we also have different IETF defined standards and RFCs, like the network programming extensions, the telemetry data collection capabilities, and a lot of open source tools which could be used to add unprecedented value to our data center or even our networks. That said, let me check the questions.
Yes, there's one question from Mahindra. Nagendra, do you want me to read out the question?
No, I can look into it. So
okay.
Application running on switch has burden on host path ASIC to CPU, which is shared by other control planes. What are the provisions for protecting? So, okay. In most of the switches, they have their own dedicated resource being carved out for virtualization, and they have internal interfaces that are not actually shared with the control plane. So this is primarily to ensure that we are not compromising with the performance of the control plane or the vendor OS being hosted on top of Linux kernel. So it's up to the implementation to ensure that we have this separation so that we are not compromising with the performance.
Nagendra, can I ask one clarifying question? As far as your network models were concerned, the 4 models that you showed, or 5 models, in fact, that you showed in your presentation, they would be exactly the same whether they are on a switch or whether they are on a server, right? These are not new. These are well-known networking models.
Yeah, right. So this could be used on routers or switches, or even if you were to do it on a server, we still can use these network models.
Correct. And just so that I can understand this a little bit better, like imagine I was not hosting this on the switch, and I had like a server which is directly connected to this switch, and I'm hosting this on that server. What is like, have you done some experiments? Like, do we really see that much advantage as we are suggesting here? Because that server is just like, it's connected directly to the switch, but instead of hosting it on the switch, I'm hosting on a server which is directly connected. What's the difference?
Yeah, so you could do it in a centralized manner where you have all these applications hosted in a server which is connected to one or two devices in the one or two switches in the data center. It got its own pros and cons. Of course, if the application is beefy, then it's really hard to say that, yeah, it is capable of hosted directly on the switches. So I think it makes sense to run it as in a dedicated server, wherein there are other applications which can really leverage the this capability. So we don't have to dedicate different resources. Rather, we can leverage the existing compute resource on these switches so that we don't need to run them on different servers. So imagine it this way: if we were to bring those applications as close as possible to the device, one option is to connect different servers to each of those switches, which is not a scalable solution. But if we have the ability to run it from one centralized server, yes, we can do it. So this is basically a trade-off between running it directly on the device, with of course its own pros and cons.
There are some more questions. Maybe it's better I don't take more time.
Yeah. So for virtualization, any developments on the micro VMs like Firecracker VM? Honestly, I don't have an answer for this. So there are some exchanges available. At least I'm aware of what's available in Cisco, where we can go and get the images, or even develop your own VM or container images that could be hosted. That could be uploaded, get it signed by or approved by the community. But I don't know if there is any work happening around micro VMs. And there are attempts in data center to turn the approach upside down, running routing ASICs in general purpose dense servers. I think so, yes. This is, I mean, with all these white box, white label boxes, yes. We are talking about running different vendor OS as part of servers. So yes, that is also possible. Again, like I said, it's going to be a long way where we'll be seeing a combination of applications running on network devices or network OS running on the servers. Are these studies that show the impact of using traditional protocols in a virtualized environment? Example, a TCP sender might spuriously time out if the hypervisor scheduling dependency is high. Yeah, so I know there are quite a few performance testing done and published different white papers in IEEE. At least a year back, if I remember it right, while I was authoring this book, just for the research purpose, I was reading some of the IEEE papers. So there are some papers that are published as part of IEEE, which might be a good source to see how different applications are performing. But again, this is something that's evolving. The application that are developed a couple of years back is not the exact same application that we are using today. There've been tremendous development to accommodate different types of architecture, or even from the virtual machine to container to even function as a service. So it's good to look into what is available now and how it is basically impacting the performance by running it in different environment.
I don't see any more questions. So thank you, Nagendra. Thanks everyone for attending. It was a really, really good discussion. Thanks for asking all the questions. And thank you, Nagendra, especially for you. It must be really late. And thanks for staying up and being here. Thanks, Tony. Thanks, Nagendra. Thanks everyone for attending. Have a great weekend.
Sure. Thank you, Drew. Thank you, Kannan. Thank you, Tony.
Kannan, do you have any last words?
No, just wanted to thank Tony and Nagendra for accepting the invitation to give a talk. Thank you, guys.
Thank you. Bye, everyone.
Thank you. Bye-bye.